All right, we're going to get going with 3.9 now. And here we're doing the derivatives of inverse trigonometric functions. So if you remember, we did trig functions, and these are the functions that essentially undo the trig functions. And so here, for example, it's asking, is arc cosine of 2 defined? And the answer here is no, because, excuse me, if we look here at the graph for arc cosine, you can see that putting in a 2, which is out here, it's never going to reach that. It never does it. This is the only values that we define it, because if we kept going, it wouldn't be a function anymore. Remember, we limited our range on this one so that we would keep it as a function. Oops, I thought that was the eraser. And so, but even so, there's never anything that you take the cosine of that's going to give you a 2. Therefore, you can never undo a 2 because cosine's never going to give you a 2. All right, whichever way you want to think of it, it's just not going to happen. So this is a big no. We're not going to get out there to 2. Same thing with arc sine. You couldn't do the arc sine of 2. It's never going to get out to 2, all right? It's never going to get out to 2 because the sine's never going to give you a 2. And then what about arc cotangent? Does arc cotangent, is it arc cotangent of 2? Is it defined? And the answer is yes. Look, if you look here at 2, on arc cotangent, absolutely, there you go. We can have a value for it. Its domain goes from negative infinity to positive infinity. It's not restricted, it's not cut off between -1 and 1 like the arc cosine and arc tangent. Okay? Next, what is the domain and range of these functions describe? Well, it's describing what values we can input and what values we can output. So essentially, we're looking at the values that we can input into regular trig functions, and they're going to be our output values for these these inverse trig functions. And we're looking at the outputs you get from regular trig functions, and they're our inputs for these inverse trig functions, okay? So just a quick little review here. Let's recall that the arctangent of x is a radian, remember radian measurements, whose tangent is x, okay? So the arctangent of x is y, is the number in -pi/2 to pi/2 for which tangent of y equals x, right? They're inverses of each other. It's an inverted function. And then the same thing for cotangent, similarly, is the number between 0 and pi. And remember, we had to restrict these in order to keep them being functions, like in sine and cosine's case. All right, so here it says, find the arctangent of 1 over square root of 3, the arctangent of negative square root of 3, and the arc cotangent of 1. I'm going to leave you to try these. It shouldn't be too hard, especially since the answers are already on this page. But just try them real quick without looking over here on the right-hand side and see if you can do them, okay? Just kind of refresh your memory on it. It's just review. This is nothing new. You should have already been able to do this coming in. All right, so let's go here. Let's picking a definition for the reciprocal. Note that there is no general agreement on how to define the arcsecant for negative values of x. We choose A so that the following is true. The arcsecant is equal to the arc cosine of 1 over x. And hopefully you remember doing that previously in a pre-algebra course or a trigonometry course. But that's what we basically came up with. It wasn't just, in other words, it wasn't this. It wasn't arcsecant equals 1 over arc cosine. It wasn't that, okay? This was not equal, okay? They're not the same thing. It was actually this that we ended up with, okay? So make sure you remember that. Again, a little bit of review. And then be familiar with the graphs. Here we've got summary of domains. Make sure you look through this and remember these domains. Again, this is stuff that should just be kind of review, refresh your mind on what these domains were. Note that the intervals are designed to avoid values where the function basically is not a function. I'm not going to write that. You can write however you want. It looks like it's supposed to be one word, but I don't know what's thinking there. But is not a function. It's or is a function, or it's designed to avoid values where the function repeats or whatever. Okay, so we're getting these intervals so that they stay as functions, because otherwise these inverted wouldn't be functions. All right, so let's take a look here. Here, we're going to want to try and find the exact value without using a calculator. I will do the first one, and then I'm going to let you do the second one. And again, you can look in the notes, and I'll have it completed in there. So this is arc cosecant, which is equal to the arc sine of 1 over 2. And then we want to know what that is equal to. So we need to essentially figure out what do we take the value of for sine that's in our domain that gives us 1/2. So if we look at the unit circle, okay, 1/2 is right here. This is 1/2. And so we're going to input something and give ourselves 1/2. So if we come across to the 1/2 line, that gives us this. That'll give us 1/2, but we also get one over here, right? So we have two places that'll give us 1/2. Now remember, for arc sine, right, we're worried about between 0 or negative pi over 2 and pi over 2, all right? So that means that we need to stay in here for our answer, which means the point that we want is this one over here, not the one there on the left. And if you think about your unit circle, you've got 3 main points over here. You've got pi over 6, which is the one we want. We've got pi over 4, and pi over 3, right? And if you remember, the coordinates for the pi over 6 one were, of course, square root of 3 over 2 and 1/2. So again, it's a good idea to remember your unit circle. And then, of course, right there, that's our sine value, and it's 1/2, meaning this answer is pi over 6. There's our answer, okay? Try doing the arc secant one yourself, convert to an arc cosine, and then look at your unit circle to find the place where you get the answer. And then I'll put the answer, I'll work it out then in the notes, and you can take a look and see if you got it, okay? So let's start actually doing derivatives. All right, so note that y equals arc sine of x is differentiable on its domain, -1 to 1, except at x equals -1 and 1. Those two places, we have vertical tangent lines, and vertical tangent lines we don't have slopes for. Okay, vertical lines we can't really take a slope for, so we're done with that. So let's try this. So we'll start with y equals arc sine of x, okay? And if we look at that, we can say that sine of y is equal to x, okay? And by doing that, we can even go and then take the derivative of it, right? Implicit differentiation. Derivative of sine is cosine. And then that's the outer derivative. Then the inner derivative is derivative of y. And then it has to equal on this right-hand side. It's essentially just dx, right? And so that's just 1. Because all we have is the derivative of x, which is dx over dx. And so that's what we end up with here, which means dy dx is equal to 1 over the cosine of y. And we don't actually want to stop there, because if we come back up to this point right here, if we come over to the side, we can square both sides. Sine squared y equals x squared, which then gives us, we can take sine squared, sine squared plus cosine squared equals 1, and make that, sine squared equals 1 minus cosine squared, right? Sine squared plus cosine squared equals 1, and you can make it sine squared equals 1 minus cosine squared. So we can substitute that in. This is 1 minus cosine squared, right? And then that equals our x squared. And then what I can do is subtract cosine squared from both sides, and then subtract x squared from both sides. So just a little bit of algebra, and you get 1 equals, not 1 equals, sorry. You get cosine squared y equals 1 minus x squared, which means cosine of y is the square root of 1 minus x squared with a plus or minus. See that? We get a plus or minus there. Cosine y equals plus or minus the square root of 1 minus x squared, which means we can come back over here and actually substitute that in for our cosine of y and get 1 over 1 minus x squared all square rooted like that. And there you go. And that pretty much gives us the derivative of arcsine. So now it's kind of a personal choice. Do you want to work this out every time you get to it and remember how to work it out? Or do you want to just, basically remember this formula down here? Note that this is when u is, the absolute value of u is less than 1, because otherwise you're outside of, of what works. You're outside the domain. So be careful of that, okay? All right. So let's take a look here and try this one here, the arcsine of x squared. And so this is going to be a chain rule thing here. We're doing the derivative of the outer times the inner. And so the derivative of the outer, if we look back here, is 1 over the square root of 1 minus u squared. So this is 1 over the square root of 1 minus, and this is what is in here. Well, what's in here is, that's our u, right? You look back over here, that's what u is, so it's going to be u squared. So it's going to be 1 minus x squared squared, because x squared is our u, right? This is what u is in that formula, okay? And then we have to multiply it by du dx, so the derivative of our u value, so times the derivative of x squared, okay? And so this is 1 over the square root of 1 minus x squared squared is x to the 4th, times the derivative of x squared, which is just 2x, and then times the derivative of the x, which is dx, which is just 1. So I won't even bother writing it this time. So ultimately, our answer is 2x over the square root of 1 minus x to the 4th, okay? And that's what this one up here equals. There you go. I'm going to leave this next one for you to try, and again, take a look in the notes to see if you're able to get it. So let's take a look at arctangent. So here we want to derive a formula to find the derivative of arctangent directly. So if we do this, we've got the derivative of the tangent of y. I'm going to take the tangent of both sides, and that'll undo that arctangent. And since y equals the arctangent of x, that means tangent of y equals x. So I'm going to do the derivative of that, kind of like we did before. Here we've got secant squared, that's the derivative tangent, is secant squared of y, times the derivative of what's on the inside. So the outer derivative was the derivative of tangent. The inner derivative is the derivative of y. And then we have to do the derivative of x, which is just, again, it's dx by dx, which is just 1. Okay? And therefore, dy dx equals 1 over secant squared y. And if we remember to our trig identities, we know that secant squared y from our Pythagorean identities equals tangent squared y, which means secant squared of y equals tangent squared y plus 1. So we can make that substitution. Substitute that in right there. So this becomes 1 over tangent squared of y plus 1. And if we look back up here, tangent of y is x, which means we can replace that tangent of y with an x. That means this becomes 1 over x squared plus 1. And that's our derivative right there. Okay? And we can generalize this down to this rule right down here, where we include the chain rule. And that's the derivative of the arctangent of u is equal to 1 over 1 plus u squared times the derivative of u. Okay, so that's, again, another important one to know. Unless you're really good at deriving them out like I just did there, then you can do it real quick, especially if it comes test time. So I'll do the first one. I'll leave the second one for you to try. Here we have the arctangent of the natural log of x. So this is going to be a chain rule. The last chain rule I just did derivative of outer times derivative of inner. This time I'll do u substitution and do the actual chain rule just so you see it. So we're going to say let u equal the natural log of x. All right. If that is the case, then y will become the arctangent of u, just like that. Du dx over here is 1 over x. That's the derivative of the natural log of x is 1 over x. And then it's times dx, but again, dx is just 1. The derivative of arctangent we just did on the previous page, so dy du is 1 over 1 plus u squared. All right, and then we come down here and we have dy dx, okay? And that equals dy du times du dx. That is equal to those two things. So then we get 1 over 1 plus u squared times 1 over x. Okay, that was this. That wasn't very good. That was this times this. That's those multiplied together. Now remember, u equals natural log of x, so we can substitute out for that u right there and get 1 over 1 plus the natural log of x squared, like that, times 1 over x, which we can combine into just one fraction. This is x times 1 plus the natural log of x squared, just like that. And that's dy dx. There's your answer. Okay? Again, you try this one here for the natural log of the arctangent of x. Kind of flip-flop there, but again, you're going to do a chain rule, whether you like to do the outer inner, like I did in the previous one, or you like to do the u substitution with the with actually writing the dy, the u's and stuff out. That's up to you, okay? I would recommend, though, that you be at least familiar with both ways. One way is quicker, and one way is, putting the dy, the u's and stuff, usually a little more thorough and helpful. All right, so why does arcsecant have an absolute value? And ultimately, this just kind of boils down to that as you go through all of this, you have these plus or minuses, right? And that's ultimately why. So so we can go on in and just kind of write a single expression for this arcsecant right there, and we can get it. I'm not going to go through all of that. You can try going through it if you want. It's all in the book, but we did the other ones. You've kind of seen how these are derived and how this is working. So the main thing you need to know is this part right here. So just for the sake of time, I mean, if you have questions on this and you want me to go over it, just let me know. But for the sake of time, you need to know this formula here. Okay, so let's try using this formula now. Let's do the derivative of the arcsecant of 5x to the fourth. Again, I'm going to switch back to doing derivative of outer times derivative of inner. And so the outer derivative is the derivative of the arcsecant. And from the previous page, it's 1 over the absolute value of u times the square root of u squared minus 1. So we're going to get 1 over the absolute value of u. Remember, this is u. U is what's inside of here. This is u. So it's the absolute value of 5x to the fourth times the square root of 5x to the fourth squared. It's a u squared minus 1. Just like that. that little line a little longer. And then we have to do the derivative times the derivative of the inner part. So times the inner part, which is 5x to the fourth, just like that. So x to the fourth is just always going to be positive because it's x to the fourth. No matter what you put in for x, you're going to get a fourth power. It's an even power. It's going to be a positive value. So we don't really have to actually worry about those absolute values anymore. So this is 5x to the fourth times the square root. 5x to the fourth squared, well, 5 squared is 25. X to the fourth times x to the fourth is x to the eighth. So there we go. And then the derivative of 5x to the fourth is 20. Bring that 4 down. 4 times 5 is 20. X to the third, just like that. And then dx, which we don't have to write. It's just 1. And then we go one more step. So these should all have equal signs. So then equals, we can now cancel out. We have an x to the third and an x to the fourth. And a 20 over 5. 20 over 5 is 4. We're left with the x to the third canceling with that x to the fourth, leaving us just an x in the denominator. And then our square root, 25x to the eighth minus 1. Okay? And there's our answer. And so I'm going to leave the next one for you to try. And if you want, take a look in the notes and see what the actual answer is. Okay? All right, here are the rest of them right there. So inverse functions and inverse cofunction identities. So make sure that you remember these. You can actually use these to do some of them. So I want you to try this. Find the derivative for the arc cosine of x using the above identity. So try doing that. And then we just move down slightly and you try and find it out. And the next page will tell you if you get it right because it's right there. Derivative of the arc cosine is right here in this chart. And again, what I'm going to say here is I highly recommend memorizing these. Okay? If it's way in the future, then you may forget them, like I forget them all the time, but have to go through and try and refigure them out. But for test time and stuff like that, it's going to be a big help to you to do it. And if you're doing enough of the homework, these should start to stick in your head, but you're definitely going to need them moving forward for the rest of the class. So I really recommend that you get these memorized so that you can go through these a lot faster and more efficiently and not have to keep stopping and trying to derive them out, which might waste time. And if you get stuck or something, then you could be in some trouble. So again, make sure that you get these memorized. Okay? And that's pretty much it. That's it. That's it for this whole section. Here are all the derivatives. Practice using them in your homework. Get them memorized. And let me know if you have any questions. All right. That's all. Thanks.